What if I told you that you can put the paint sample boards down and stop struggling to see undertones? What a sense of relief, right? It's true. You don't have to subject yourself to the visual gymnastics that so many people insist are necessary in order to get the color design results you want. You don't need to learn how to see color, whatever that's supposed to mean, because the vision system you have works perfectly fine. What you don't have is a system to judge color and a simple process to explain why it looks the way it does. My name is Lori Sawaya. I'm a color strategist, and I have an online color training program called Camp Chroma. The transformation you experience when you train with me isn't about trying to change how you see color. What transforms is how you evaluate how color actually looks. Instead of talking about only one component of that system, we're going to talk about several, or we could say several useful pieces to help complete the puzzle of how color works. It's a mashup of information I wish I would have figured out a lot sooner than I did. I'm sure everyone here can relate to how long it can take to research anything about color. So we're going to kick things off with a couple of my favorite time savers. Number one is the settings cog at the bottom right of video frames. If we click on it, we can choose the playback speed, and I'm going to show you how that works right now. I'm going to grab my mouse. I'm going to start the video, and right down here you can see that cog. If we click on it, here's playback speed, and we can choose to slow down or speed up. I'm going to choose number 2, and we can watch the video in double time. And like I said, you can choose to speed it up or slow it down. And this is really handy because if you speed it up, you can watch a video in a fraction of the time it would take to watch compared to normal speed. So you can watch a 4-minute video in like 2 minutes. Another time saver that I love is you can make an icon for your phone or tablet for any website so it opens like an app. For example, I made an icon for my discussion forums on the Land of Color, and I also made one for easyrgb.com, which is another website that I visit often. Creating an icon is really easy to do. Just Google how to add an icon for any website to find directions for your device. And speaking of devices, we can't talk about saving time without talking about the ultra-portable devices like you see here. One of the questions I'm asked most often is which device I recommend, which one is the best. They all work basically the same way, so a lot depends on the design of the app that works with the device and what kind of projects you want to use it for. I happen to prefer the variable ink products, which are Color Muse and Spectra 1. I include a Camp Chroma branded Color Muse in the kit that we ship to your door when you sign up for my course because it's a good introductory device priced at just $60. And I love the design and function of the app. A Color Muse is a colorimeter, and it's plenty accurate and powerful enough for an architectural color design workflow. Something to note is devices in a similar price range like NYX Mini measure color using a D50 illuminant. There isn't an option to change the light source. It's worth noting because the industry standard illuminant for architectural coatings is D65. That's what all the paint manufacturers use to make their colors and their color collateral, like paint chips and fan decks. For some applications, this might be an issue, but for an architectural color design workflow, it's really not a problem because the results you get with D50 and D65 are pretty close. They're very similar. They're close enough. And a designer is at the end of the workflow to make visual judgments and those final color decisions. I personally use the Spectra 1 or Spectra 1 Pro depending on what I'm measuring. I use the Pro device for any surface that has a shiny or gloss finish and the Spectra 1 for pretty much everything else. One of the key reasons why is with the more expensive devices, these cost about $300 each, you get more features in the app, like spectral curves and Metamerism alerts. Again, the difference between a Spectral 1 and Spectral 1 Pro is the Pro version accounts for gloss. So you can measure glossy tile or countertops, for example. In technical terms, the difference is specified as the Spectral 1 is specularity excluded and the Spectral 1 Pro is specularity included. For example, the easyrgb.com website uses instruments with sphere geometry and specularity included to measure colors. So if you are using data values from easyrgb to compare colors, which I recommend, that's a great way to use that website, I recommend the Spectral 1 Pro because it also measures color with a sphere geometry and specularity included. So in other words, the Spectral 1 Pro is the most similar to easyrgb. The app design for the Spectral 1 devices is the same as ColorMuse, which is great. I love the consistency, but only the app for the Spectros displays spectral curves and Metamerism warnings. And this first slide right here, you can see the spectral curves, and this next one coming up is the Metamerism warnings. And that's because the Spectral devices are spectrophotometers and they capture more detailed information, which is different from how the ColorMuse works because it's a colorimeter. Without getting too technical or boring, the basic difference between a colorimeter and a spectrophotometer is a colorimeter captures the overall important parts of color, and a spectrophotometer gets more wavelength specific and provides more data points, so you can do more things with it. So to answer the question, which device do I recommend? I'd say ColorMuse is good for a beginner, Spectral 1 if you know you're not going to be measuring glossy surfaces, and the Spectral 1 Pro is the device for you if you want to kind of cover all the bases. The Spectral 1 Pro is the newest device from Variable, and right now it can kind of take a minute to get one because demand has been crazy. There are many ways to streamline the steps in the color design process with these high-tech color tools, and I'm going to show you the easiest and most useful right now. Understanding a color's characteristics is important for several reasons, like communicating to other people what it looks like, or figuring out harmonious color relationships, like what colors go together, especially how do you know what neutrals go together? That's a question I'm asked a lot. And this is where a color wheel can help. And this is where these handheld devices really shine and are super time savers because you can scan a color and the information in the app will tell you what hue family that color belongs to. You can get a read on a color's factual hue family in a matter of seconds. Let's use this quartz sample so I can show you what I mean. I measured light and dark areas on the sample, and if we swipe left on the app, we can get a new window with LCH values. We're looking for the H value because H is for hue angle. The lighter area has a hue angle of 99.94 and the darker area has a hue angle of 91.6. When we plot those angles on the Color Strategist color wheel, we can quickly see that these colors are near neutrals from the yellow hue family. From here, we can move forward in the design process and confidently look for paint colors and other materials that we know will relate to and coordinate with the exact colors in the quartz. At this point in the conversation, you might be wondering what LCH is and how does the H indicate hue angle. LCH refers to values within the CLAB color space. It's hard not to stumble on CLAB when you Google for information about how color works because literally everything that is colorful has a CLAB value. and every industry you can name across the globe uses this color space to make and manage color. CLAB is shorthand for the CIE 1976 L*, A*, B* color space that was introduced by the International Commission on Illumination. That was a lot to say. I'm glad we have a shorthand version. The CIE is a 100-year-old organization that creates international standards related to light and color. There are two ways to illustrate and notate colors within the CLAB color space. One is LAB and the other is LCH. I'm not going to get into the details of LAB and LCH values beyond what we've already done, which was showing you how to get the hue angle from the ColorMuse app and how to use it to determine a color's hue family. Because some of you probably already understand the CLAB color space, and if you don't know what it's about, it would take more explaining than we have time for today. The one thing I wish I would have understood about CLAB sooner than I did is that CLAB refers to the color space itself, and LAB and LCH is how to notate colors within the color space. Getting CLAB, LAB, and LCH sorted out was extremely helpful for me because it made it so much easier to understand and decipher the more technical color science papers and resources. The reason why the CLAB color space is formatted two ways is because the LAB Cartesian coordinates are awesome for comparing colors and seeing how colors are specifically different, but they're not so great for helping you to visualize what a color looks like in your head. LCH notations define and describe color appearance in a more relatable way. Since the Munsell color order system was the template for the CLAB color space, it was possible to align notations with Munsell hue value chroma, and the result was CLAB lightness, chroma, and hue, also known as LCH. It's also why I was able to combine LCH hue degrees and Munsell hue families into one color wheel that I named the Color Strategist color wheel. Getting proficient at visualizing color in your head is a matter of remembering that a color wheel, in this case the Color Strategist color wheel, is just one slice from the middle of a color space. The high chroma hue parents featured on the wheel represent complete families of colors. When you understand a three-dimensional color space like CLAB and Munsell, you know that every color has a place and notation within the color space. Here's another way to look at all the colors the hue parents on the wheel represent. We'll start with fully chromatic hue family neighborhoods that I placed on the outside of the color wheel and scroll through a gradation all the way down to colors of white. This is what the full chroma hue family neighborhoods look like, and we're going to keep bumping it down in chroma. So here's the first step down. This is another bump down. Now the colors are getting more noticeably muted. Progressing closer and closer to neutral. And here we get an idea of what chromatic grays from each hue family look like, each hue family neighborhood, I should say. And here's a lighter view of those chromatic grays. Another bump down in chroma and a bump up in lightness gives us a sense of what near neutrals from each hue family look like. And finally, this gives you a look at a full gradation of whites all the way around the wheel. There are colors of white and gray from every single hue family. So just because you don't see all the different tints, tones, and shades literally on a color wheel, know that they are implied and represented by their hue parent. Transforming values to a Munsell hue value chroma notation involves mathematical interpolation and lookup tables. And yes, it is as complicated as it sounds, but the good news is you don't have to know or understand any of that. You just need to know what to do with the results. One of the anomalies, or as I like to affectionately call them, areas of uncertainty, is in the blue region. Specifically, the blue to purple blue, or 235 degrees to 290 degrees-ish, is the area of greatest uncertainty when aligning LCH with Munsell hue families. Being aware of this area means you know to trust a notation a little less with colors of blue and visually assess a little more. You can always depend on your color mojo to fill in the blanks where the science is weakest. And that applies to using a framework of color notations in general, not just when it comes to known areas of discrepancy in the system. The thing about the areas of greatest uncertainty with Munsell and C-Lab is that they don't impact specifying color for the built environment all that much. The discrepancies aren't that big of a deal for our application because the average color strata for the built environment is mostly lighter to midtones where there's the least amount of uncertainty. Also, the colors we use are mostly near neutral, chromatic grays from the yellow to green hue family region, precisely where there is the least amount of discrepancy overall. Where there is the most uncertainty, blue to purple blue, mid-tone to darker colors, is the region of the spectrum that we specify the least. Another important nugget of information about the blue hue family neighborhood is 5B, the middle of the blue hue family. It isn't your typical color wheel primary blue. Instead, it's bluish green. It's bluish green for spacing reasons necessary to get equidistant spacing of Munsell hue families around the wheel. Benjamin Moore's teal 2055-10 is a little on the darker side, but it's still a good physical example of a 5B color. If you grab a chip, you'll see that it leans greenish. It's not just blue. If you're looking for a typical primary blue, you're going to find it in the 245 to 250 degree range on the color wheel. One of the reasons this adjustment works is because a hue circle is an interval scale with no defined point of zero. You can see on this poster from Munsell Color that they explain the greenish slant of 5B by aligning it with the color of cyan ink. I thought that was kind of a genius way to communicate what it looks like. You'll notice on most color wheels showing Munsell hue families that the number 5 is emphasized somehow. That's because the number 5 marks the point where the highest concentration of the respective hue parent is perceived, and that's usually marked with a big dot. I chose to do the same thing when I designed my color wheel. And you will find all kinds of color wheel designs featuring Munsell hue families. This is a picture one of my Camp Chroma students sent in. She found it in a book about how the Munsell color order system works, and she was confused about the numbers on the outside of the wheel. She wanted to know what they were. She knew that they didn't indicate degrees or hue angles because she had learned about LCH in my course. When you come across a Munsell color wheel that looks like this one, know that those aren't angles or degrees. Those are units of hue family, starting at 1R. R means the red hue family. There are 100 units, 10 per hue family. Some describe this arrangement as hue ranges divided into 10 subzones, splitting the color circle into 100 perceptually uniform hue segments. The best way to format Munsell hue families into a color wheel is open to interpretation, just like a lot of things about how color works. But the bottom line is, no matter how the hue families are illustrated, the hue value chroma notation will be consistent and repeatable. Everyone will be on the same page when it comes to the notation. The notation will be consistent because everyone is working from the same core system of factual color definition and order. So far, I've mentioned factual color a couple times. Let's take a few minutes and explore what I mean by that. I'm going to tell you something that I don't tell a whole lot of people because it's not a very popular opinion, but I'm not a huge fan of Joseph Albers. I think his small square on big square color effects theories are meaningful to fine artists, like, people who paint, but they don't translate to the built environment. The proximity of color isn't that literal in a three-dimensional space. I heard someone call them clever parlor tricks once, and that really resonated with me. Your mileage with the square on square concept may vary from mine, and that's perfectly okay. However, I found Albers' take on factual versus actual color kind of brilliant, and I have adopted a version of that concept into my own color point of view. Sarah Loengard explained Albers best in a paper titled Explaining Color in two 1963 publications. Here's what she said. Albers called for a separation of what he called factual facts from actual facts. While a factual fact may be taught in the classroom or valorized by color scientists working to quantify the visual experience, an actual fact is directly connected to experience. Albers' interest was the actual facts, what viewer experience shows to be true, rather than what the scientist or mathematician declares to be so. Color measurements, data values, notations, whatever you want to call them, are indeed factual. Part of what makes them factual is they're repeatable. In our separate locations, we could be miles and miles apart, we could both measure a Benjamin Moore paint color, for example, and we'd get very near identical results. And we could easily agree with the numeric definition of that color. In real-world architectural color design application, factual color is a first approximation of color appearance. Actual color is what happens when the color is installed. Both factual color and actual color are important pieces to the puzzle of how color works, because if you understand how a framework of factual numeric color descriptions work, like a hue value chroma notation, you can use that framework. You can use it as a jumping off point to better understand, predict, and manage how color actually renders in a space. Ironically, it's the defined light source used to determine numeric color descriptions that makes a framework of notations elastic, with built-in flexibility to account for and explain why and how color shifts in different light sources, and how and why color is perceived differently by different people in different contexts. Because of that flexibility, color measurements in actual color design application are the furthest you can get from rigid, formulaic, or prescriptive. Factual color stands in stark contrast to theories like it's possible to categorize color according to perceived undertones, because undertones are just someone's subjective opinion of how a color actually looks to them under unspecified light sources in a particular context. When people use the word undertone, they're describing their response to an amount of discernible hue in a color. Because it is subjective, there's no guarantee that description is going to scale beyond their own perception. Which is why collecting these two final pieces of factual and actual color is a good way to wrap up our webinar today. There's no question about the power and usefulness of a factual framework. But at the same time, it's important to remember the words of Fred Billmeyer Jr., who said, "Nobody accepts or rejects color because of the numbers. It's the way it looks that counts." That's my very favorite color quote, and I like to squeeze it in wherever I can. I hope you find the information that I shared in today's webinar helpful and useful, and thanks for choosing to spend some time with me talking about color. I hope I'll see you next time.